Okay, in this tutorial we're looking at section 9.6, which is about solving type 4 differential equations, which are in the form d squared y on dx squared equals f of x. So for type 4 differential equations, we simply have to integrate it twice. Okay, each time we integrate, we're going to get a constant of integration. So the first is c1 and the second is c2. Okay, it's just the notation we usually use. Okay, this means if we want to find a particular solution, we're going to have to find both our C1 and C2 values. Okay, so we need two pieces of information to find them. Okay, so we'll need two pieces of information, and what we'll do is actually use the information that we're given to find C1 after we've done the first integration. Okay, and then when we do the second integration, we get C2. We'll use our second bit of information to get its value. Okay, one of the applications of this is beam deflections. Okay, so this is an example of a type 4 differential equation. We've got two cases where one end is fixed, okay, and so the beam sagging down at one end, or both ends are fixed and the beam sags in the middle. Okay, and so the way and the path that they bend can be demonstrated or described using one of these type 4 differential equations. So we may as well get stuck straight into some worked examples. So the first one we're looking at is worked example 16. Okay, and we need to solve d squared y on dx squared plus 36x equals 0, given that y of 1 equals 3 and y dash 1 equals 2. Okay, so we need to obviously rearrange this equation. So we can see our d squared y on dx squared equals negative 36x. Okay, that means then that dy dx going to be the integral of negative 36x dx, okay, which is going to be negative 18x squared plus c1. Okay, because we found dy dx, we need to use our information of y dash to find c1. So we say when x is 1, y is 2. So we can say, well, 2 okay, is equal to negative 18 times 1 squared plus c1. Okay, so that means then that we're going to be, we can make it 20 equals C1, okay, just by adding on our 18. Okay, so that means that our dy dx equals negative 18x squared plus 20. So that means that y equals the integral of negative 18x squared plus 20 dx. Okay, so when we integrate that, we're going to get that we're at negative 6x cubed plus 20x plus c2. Okay, now we need to use our other information. So when x is 1, y is 3. So we can say, well, 3 equals negative 6 times 1 cubed plus 20 times 1 plus c2. Okay, so it means we've got 3 equals minus 6 plus 20 plus c2. So it means c2 is going to equal negative 11. Okay, therefore our y is going to equal negative 6x cubed plus 20x minus 11. Okay, and we're done for this worked example. So we'll keep moving on. We have a look at worked example 17. Okay, we're solving d squared y on dx squared plus 2 on 2x plus 9 cubed equals 0, given that y of 0 equals 0 and y dash of 0 also equals 0. Okay, so the first thing we need to do is rearrange this, so we get our d squared y on dx squared is equaling our negative 2 over 2x plus 9 cubed. Okay, so that means we're going to get our dy dx. Okay, we need to integrate negative 2 outside of 2x plus 9 to the power of 3 dx. Okay, and we can rewrite that as minus 2, integral of minus 2 times 2x plus 9 to the negative 3 okay, dx. Okay, so dy dx okay, will equal our, so what we do for this one is we increase our power, okay, by 1, which will make it negative 2. Okay, and divide it by -2 times our 2. Our -2 here will cancel out with our 2 here, our -2 there. Okay, so we'll just have this 2 from there on the bottom line as well. So we'll get, in the end, we get 1 over 2 times 2x plus 9 squared plus C1. Okay, so we use our derivative information. So we say, well, 0 equals 1 over 2 times 0 plus 9 squared plus C1. Okay, so when we rearrange this, we get C1 equaling negative 1 on 162. So that means our dy dx is equal to 1 over 2 times 2x plus 9 squared, like minus 1 on 162. Hey, so now we need to integrate that. So we're going to be integrating 2x plus 9 to the negative 2 over 2 minus 1 on 162 with respect to x. And we'll get y when we do that. Okay, so when we run through with that, okay, we've got to increase our power by 1. Okay, we've got to divide by that negative 1 and by 2. Okay, so we're going to end up with negative 1 over 4 times 2x plus 9, okay, minus x over 162, okay, plus C2. Okay, again, we're going to let x and y equal 0. So 0 equals negative 1 over 4 times 0 plus 9 minus 0 plus C2. So C2, when we rearrange, we find is 1 over 36. Okay, so we can build up our equation now and say y equals minus 1 over 4 on 2x plus 9. So minus x on 162. Okay, plus 1 on 36. Okay, now for this one they want us to simplify it further, so what we need to do is make our denominators the same. Okay, so what we need to do, okay, is we end up, when we make our denominators the same, end up with minus 81 minus 2x times 2x plus 9 plus 9 times 2x plus 9 all over 324 times 2x plus 9. Okay, so that's making our denominators the same. Okay, so a little bit messy that one, but what we're going to do is you could expand out our top line, all our brackets here, make it negative 81 minus 4x squared minus 18x plus 18x plus 81 when we expand all that out, and that's still over our 324 times 2x plus 9. Okay, well, our minus 81 and 81 cancel out, and minus 18 and x and 18x cancel out, so we're left with minus 4x squared over our 324 times 2x plus 9. Okay, and we simplify our 4 with our 324, which leaves us with minus x squared on 81 times 2x plus 9, and we're finished. Okay, so all this process I don't think was too difficult to get to this step. Okay, and then it's just a bit of our algebra work and rearranging to simplify it down. Okay. So we've got one more worked example I'm going to have a look at, which is worked example 18. Okay, so a beam of length 2L rests with its end on 2 supports at the same horizontal level. The downward deflection on y, okay, from the horizontal satisfies the differential equation d squared y on dx squared, okay, equals kx times x minus 2L, okay, for 0 is less than or equal to x is less than or equal to 2L. Okay, where x is a horizontal distance from one end of the beam and k is a constant related to the stiffness and bending moment of the beam. Okay, we need to find the deflection y in terms of x and show that the maximum deflection occurs in the middle of the beam. Hey, so what we're doing here for that part is we need to actually go through and find our equation for y. So we need to look at this, and we need to go, well, we need to multiply it through by our x. Okay, otherwise we have problems. So k outside of x squared minus 2lx. Okay, and we're going to integrate that. So our dy dx is going to be the integral. Now we bring our k out because it's a constant, so we can say k outside of x squared minus 2lx dx. Okay, well, when we integrate that, will be k outside of x cubed on 3, okay, minus lx squared plus c. So lx squared plus c1. Okay. So what we can do now, okay, is since the beam is fixed at both ends, okay, when x equals 0 when y equals 0, and y equals 0 when x equals 2L. We could not determine the first constant integration at this stage, okay, so we've got to actually keep going. Right, so we can't actually do anything with our C1 yet. We'll keep going. Okay, so we need to integrate again. So I can say, well, y equals, okay, well, we can bring our k out the front still, okay, and integrate our x cubed on 3 minus our l x squared, okay, plus our c1, okay, with respect to x, okay, and we're going to get our k outside of x to the 4 on 12 minus lx cubed on 3 plus c1x plus c2. Okay. So what we can do, okay, is we're going to end up having to set up some simultaneous equations. Okay. So what we need to do is, well, we know with our second constant of integration, okay, well, we can use when x equals 0 and y equals 0. Okay. So we know that, and sorry, I've got the brackets here. Okay, so we know that we can make x and y equal 0, okay, because our beam is fixed at each end. So when we do that, we can see straight away, well, everything cancels out, so C2 equals 0. Okay, so what we now need to do to find C1 is use the fact that y equals 0 when x equals 2L. Okay, because that's our other end of our beam, is when x equals 2L. That's our other end of our fixed beam. Okay, so what we do then, okay, is sub in 0, but our k equals, well, it's going to be 16 L to the 4, okay, on 12 minus L times 2L cubed on 3 plus 2LC1. Okay, so when we do that, okay, we can find that C1 equals 2L cubed on 3 when we rearrange that for C1. Okay, so we've managed to do that. Okay, so we want to simplify our solution now. Okay, by subbing everything back in, well, we can really say now that our y, okay, is equal to our k outside of our x to the 4 on 12 minus lx cubed on 3 plus 2l cubed on 3x. Okay, and we can simplify that, okay, and say then that we've got k on 12 outside of x to the 4 minus 4lx cubed plus 8l cubed x. Okay, so that's our equation, okay, for y now. Okay, but what we also need to answer, okay, was find the deflection in y in terms of x and show that the maximum deflection occurs in the middle of the beam. Okay, so what we need to do now is actually find our first derivative of this. So we're actually now looking at dy dx, okay, and well, we'll know that that's going to become our k on 12 outside of 4x cubed minus 12lx squared plus 8l squared. Okay, well, we've got a 4 in everything here, so we can simplify this and make it k on 3 outside of x cubed minus 3lx squared plus 2l cubed. Okay. Now, we want to show that our maximum deflection occurs in the middle of the beam. Well, our beam, remember, is 2l in length, so the middle of our beam is when x equals l. Okay, so we can substitute in x equals l. Okay, so that means that dy dx equals our k on 3 l cubed, take 3l cubed, plus 2l cubed. Okay, which means we're going to get 0. Okay, which is exactly what we want. This is all going to cancel out. Okay, so we can say then that yes, because that's when our derivative is equal to 0. Okay, then therefore deflection does occur. So therefore max deflection, it should be max deflection occurs in the middle of the beam. Okay, now we want to actually know what the maximum deflection is. Well, we know it occurs when x equals L, so this is our equation that gives our deflection, so we need to put x equals L into this equation. This is k on 12 outside of L to the 4 sorry, they've just up this up slightly. L to the 4 minus 4L to the 4, okay, plus 8L to the 4, okay, is what we'd end up getting there, okay, which means we're k on 12 outside of, well, we've got L to the 4 minus 4L to the 4 is negative 3L to the 4 plus 8L to the 4 gives us 5L to the 4. Okay. Means we're going to get, if we look at this, we can say, well, we're 5k L to the 4 on 12. Okay, is going to be our maximum deflection. Okay, in the textbook they accidentally use L to the power of 3, okay, by mistake, but they get our numbers correct everywhere else. Okay, so that is the last worked example for this section. Okay, certainly the beam deflection worked example was a little bit more involved than the other ones. Okay. However, I think you'll actually go okay with these questions, okay, with a little bit of persistence.